This is a form of video documentation for an off-axis digital holography library that I've written, which I'm calling digHolo. I'm told this logo reminds some people of another proprietary logo, but I can assure you that I don't know what you're talking about. This is a legally distinct piece of my own artwork. I've made an earlier video on off-axis digital holography that explains the technique, but I'm presuming that if you're interested in the library, then you already know what off-axis digital holography is. Very briefly, it's a technique for measuring optical fields by interfering the field you want to measure, so-called object wave, with a reference wave. That reference wave is typically a quasi-plane wave coming in at an angle relative to the object wave. You measure the intensity of the interference between those two waves, the object and the reference, on a camera, and you process that interferogram digitally to recover the field. That is, you recover the spatial amplitude and phase of the object wave. And that's what this library is for doing that process. You feed frames into the library one at a time, or preferably in batches, so it parallelizes better. And then it will spit out reconstructed fields. It'll give you reconstructed fields in terms of pixels, like we see here, but it can also do a Hermite-Gaussian modal decomposition of the field, and it's particularly quick at doing that. I'll get back to speed and run some benchmarks in a moment. But this library is written in C++11, and it should be suitable for any x86 machine that supports AVX2 and FMA3 instructions. So that's mostly CPUs after about 2014. You can run it on Windows or Linux, and there's a precompiled statically linked DLL for Windows is provided, which you should be able to use as is. Its dependencies are IFFTW and a BLAS/LPACK compatible library like Intel MKL or OpenBLAS or similar. You can compile it as a DLL/shared object, but you can also compile it as an executable and call it from the command line. There's 3 usage examples that are provided. We've got a Matlab one, Python, and C++ as a Visual Studio project. I'll go through the Matlab example later. The Python example is basically the same. The header function is also fully documented for every function, every definition, and derived from that is the 90-something page PDF user manual. At the time of this recording, the library is purely CPU based. It's not GPU accelerated, but it is quite fast. It's fast enough that there's a realistic chance on a decent machine that the bottleneck will be getting frames off the camera, not the digHolo library, at least when frames are processed in batches. This graph here illustrates how many frames per second can be processed using an Intel Core i9-7980XE CPU, and it is or was a good high-end desktop CPU from late 2017. It's got 18 physical cores. And if we look at the green series on the plot, where we take a 1024 by 1024 section of a larger camera frame, process it, and return the corresponding 336 by 336 pixel reconstructed field. As long as you're processing at least as many frames as there are CPU cores, it can process about 1600 frames per second. So if your pixels are 2 bytes each off the camera, that works out to be about 26 gigabit per second. The other benchmarks for different sizes saturate at a similar sort of level around that 20 gigabit mark on this particular machine. It's not as optimized for processing single frames, but it can still process a single frame one at a time, 1024 by 1024 pixels. You can get about 100 frames a second, which is like 1.5 gigabit per second of raw camera data flowing in. However, where the library is particularly impressive, I think, is its ability to extract Hermite-Gaussian modal coefficients or related spatial decompositions. Here, if we imagine we've got a field that's 336 by 336 pixels, and we want to extract the Hermite-Gaussian decomposition of that field, for large batches of frames and high numbers of modes in the decomposition where the parallelism is favorable, we can see that on a per mode basis, it works out to be 70 million modal coefficients per second. On the small 32 by 32 size, it's about a billion modal coefficients per second. So that's billion with a B, 10 to the 9. So imagine you've got 1,000 fields that you extracted from 1,000 camera frames, and now you want to extract the first 1,000-ish Hermite-Gaussian modes from those fields. The rate is 36 million per second, so the total time for the whole decomposition of that whole 1,000 frames would be about 30 milliseconds. Well, the inverse of that would mean that you can process the whole batch at a rate of 36 Hertz. So that would mean that if you had to feed in the corresponding 1024 by 1024 camera frames at the start, that would be at a rate of 36 kilohertz. So that would mean you'd have to have 1024 by 1024 camera frames coming in at a rate of 36 kilohertz before you saturate the modal decomposition routine, which is fairly obscene because your camera bandwidth would have to be like half a terabit per second to do that. Okay, let's have a look at the basics of what this library does and the processing pipeline stages it uses to take our recorded interferogram, our digital hologram, and then process that to extract the corresponding optical field. Here we have our raw camera frame containing the interferogram. That's the intensity of the interference between the reference wave and the object wave. The processing pipeline starts with a frame or batches of multiple frames to be processed. The software supports both single polarization and dual polarization modes. The example I'll be showing is for this polarization diverse case, where our camera frame actually contains two interferograms, one for each polarization component. So in the lab, this typically means we've got something like a Wollaston or a calcite beam displacer installed so that we can split up the object wave into the two orthogonal polarizations and analyze both. If you're working with two polarizations, particularly if you're using the AutoAligh routine, which I'll talk about later, to automatically find your parameters, then you want to have the two polarizations on separate sides of the width of the camera frame. So that's how you can indicate that they're two separate interferograms. But if you're just doing single polarization, then you'll just have one interferogram per frame. We've got frames of size frame width, pixels wide, by frame height, pixels high, and then the position axis of the frame in meters has the 0 point in the middle. And then the physical dimension will depend on the number of pixels and the physical size of those pixels. So i.e. the physical size of your actual physical camera CCD pixels. And then, like I said, if you're working with two polarization components on the same frame, you should put them on opposite sides of the camera like so. You'll be selecting a sub-window of the total frame for the actual interferogram. If there's two polarizations, then the dimensions of both polarizations are the same, IFFT window size X and Y in pixels. That'll be the part of the camera frame that's actually Fourier transformed at the very start of the process. We Fourier transform those windows, and then we end up in the Fourier plane, funnily enough, for one or both of those polarization components. Now we're in K-space, that is the spatial frequency domain, or equivalently the angle domain. We pick off the off-axis term, which is positioned at some location in Fourier space corresponding to the physical XY incident angle of your reference wave relative to the object wave. A particular window in Fourier space is selected of a given angular radius. That's inverse Fourier transformed, and any residual tilt of the reference wave is removed to give us our reconstructed fields. Now we're back in the camera plane with the fields for one or both polarizations. There's then an additional optional processing step where you can take those fields and instead of expressing them as an amplitude and phase value for every pixel, you express it as an amplitude and phase value for every Hermite-Gaussian mode in a modal decomposition, or some other basis like Laguerre-Gaussian or some other related basis that you can specify as the user. Looking here, this is the coefficient matrix, not just for a single frame, but for a whole batch of frames. And our single frame here would be just one row of that matrix like so. It's just one vector that lists the amplitude and phase of every mode for that particular camera frame, that particular field. Next, let's look at a simple example using the provided Matlab example script, and the Python script is essentially the same. Now in Matlab, there is one little quirk to it, and that is for the header, we'll have to go down and uncomment this line. That's just because Matlab doesn't seem to like using non-standard C types. Python doesn't have a problem. So just my complex numbers, it seems to get a little bit confused by. So I've got that little flag in there for use in Matlab. Let's just run it, see what happens. Okay, there we go. So we can see the camera frames at the top, the corresponding fields at the bottom. That's the basis that it's used to decompose the fields. That's an optional step. And now we get a viewport, which is like the simple plotting function which is available straight out of digHolo. We get the transfer matrix. So this is like frames versus the HG coefficients for each of those frames. And the basis, that's the HG basis it used to decompose in. And then that's the raw camera frames, that's the raw interferograms. And then that's the reconstructed fields. So this reconstructed field for this particular frame would be this last list of coefficients here. Okay, so that's the basic sort of usage. We can sort of scroll through the code, have a look, and as I said, the Python one's pretty much the same. First up, just loads the DLL. Makes sense, this is a Windows machine. Then it's got how many camera frames we want. In this test example, I've said 45. The width and height of the frames in pixels, and the pixel size, so the physical pixel size of the camera pixel, which is 20 micron in this case. Number of polarization components per frame, 2. It's a dual polarization example. The wavelength, 1565 nanometers. We've got the size of the IFFT window, so that would just be the window around here that we want to select. To actually do the IFFT. Verbosity, just saying how much do we want to print out to the console. So 2 is pretty verbose, prints out most things. Resolution mode, it's set to 1, which is the low resolution mode, which just means that when it's reconstructing the fields, it doesn't oversample. Right, so you can see it's only got the same resolution as the window in the Fourier plane that you IFFT to get here. It doesn't have the same resolution or same number of pixels as the camera frame of which it originated. Same information though. We've got the number of Hermite-Gaussian mode groups to include, 9. We've decided to redirect the console to file, and that's the name of the file. We've decided that we want to make the viewport view function number 8. You'd have to look at the header to work out what number 8 is, but that looks to me like it's the sum of all fields. Okay, and then you get to the actual crux of the function, of the usage, sorry. So we start off with, in this case, it just creates a bunch of test frames, but these would be frames that would normally come out of your camera. It creates a digHolo object, starts up the pipeline, returns a handle that we can use to pass to the future functions. Then it starts to set up a bunch of the parameters that we had above. Then it's going to say that we want to auto-align everything. We're going to set a batch count, which was 45 frames from before. Then we run the auto-align. And then not sure why I reset the batch here, but it doesn't hurt. I guess the frame pointer could have moved. And we call the process batch, and then that will run the whole pipeline. It will actually already have been run when we run digHolo auto-align. But let's say I was changing the frame to a different bunch of frames, and then I call digHolo process batch, and I can reprocess a new bunch of frames, which in this case is just the same as the old bunch of frames. But theoretically, you could have changed the frames in between. I won't look at the view batch summary. That just gives you a bunch of parameters that come out. And then it extracts other things, like you can get the fields out, get the basis fields, etc., etc., all the stuff that we viewed. Now we can see inside the folder, we've got this very long file name, which is just where the FFTW library stores its wisdom, so to speak. And we've also got the console. We can probably open up the console in here. We've got verbosity mode 2, which means that it's printing out most things. And we can have a little run through of the kind of things that it prints out. So it's starting to run the AutoAligh routine. That's basically the first thing that it runs. It's going to try to estimate the parameters for the digHolo. So, things like the tilt, the beam center, the defocus, the size of the waist if we're using modal decomposition. Just gives us a little printout of our system settings, of our system environment, what kind of CPU we're running on, etc. Batch count of 45. Does an IFFT. Takes a guess at what the tilt is, which seems to be pretty close to the answer right off the bat. Takes a guess at where the center of the beam is on the camera. That also seems to be pretty close right off the bat. And we can see here that it's cycling through. In this first kind of section here, it's taking a bit of a guess at what the tilts are, what the beam centers are, what the size of the waist of the HG modes are, what the defocus is. Having a bit of a guess at all of those. And it has that first initial parameter estimate. In this case, it's taken 138 milliseconds. And then it moves on to tweaks. So this one, it tries to rapidly lock on to a pretty good guess. And then if you've selected that type of AutoAligh routine, it'll go through and actually try to tweak the parameters and sort of do like an optimization search to try to find optimal parameters. And that's what this section here is. Keeps trying to improve the parameters, and in this case the insertion loss, the total power, keeps getting better and better and better, but not by a lot. Alright, and then it is done, and you can see it prints out here and it says the completed alignment occurred in 306 milliseconds, so at a rate of 3.26 hertz in this case. Gives you a summary of how many times it called each routine while it was doing the AutoAligh. Then it's done, and then in this case it's also doing a benchmark. So it gives us a little printout of how fast each of the little subroutines are running. Most of the time is actually spent just doing that first FFT. And then it's done. And it redirects the file back to standard out. So that's just a little example there of how to use the digHolo routine in Matlab, and the Python example is pretty much the same. Next, I'll run through the basic usage patterns and the kind of functions that are available at time of recording this video. The first thing you'll need to do is to ask the library to create a new digHolo object and its associated pipeline. You can have multiple pipelines on the go at once if you want, and they should all be thread safe. They've all got their own memory. So we breathe life into the digHolo object. That object's really handled internally by calling the digHoloCreate routine. And that just returns to us an integer, which identifies which pipeline that refers to. And we'll pass that integer to just about every digHolo function after this so that it knows which pipeline we're talking about when we're sending instructions. Afterwards, when you're done with the object, we should destroy it to free up its associated memory. Likely the next thing you'll have to do is tell digHolo where the frames are. Ideally your frames should be single precision float 32s. Your camera is probably giving you integers in the lab. There are routines to specify the buffer as an unsigned int16 array. But there is a performance penalty associated with that because the FFT library needs float 32 inputs. So your best bet is almost certainly going to be converting your frames to float 32 as you get them off the camera, or soon after you get them off your camera, rather than getting digHolo to do it for you, especially using AutoAligh. Alright, so we specify where the frames are in memory, and then you'd probably want to specify the size of the frames in pixel dimensions, so width by height. Then specify how physically large each pixel is on the camera. For example, it might be 10 micron. The processing will actually work even if you don't specify this. It'll just choose some default value. But if you want the parameters that you get at the end to be physically meaningful, like tilts, angles, defocus, beam centers, etc., then you'll have to put in proper dimensions for your pixels. So you can still get fields out, but the dimensions will be all incorrectly defined without the proper pixel pitch. Similarly, you'll also have to set the operating wavelength. Again, processing will work without it, but in order to convert spatial frequency to k-space to angles in a physically meaningful way, you'll need to specify what the wavelength is. Another thing you want to specify is the number of polarization components, 1 or 2. There's also the number of frames per batch count. This defines how many frames will be processed together as a batch during one process pipeline run. Okay, now we get to the key parameters that need to be specified for off-axis digital holography to actually take place. Effectively, they are: where is your object wave and what is your reference wave? Where is your object wave on the camera? Where is your reference wave in Fourier space? And optionally, you can also specify things like if your reference wave is a bit out of focus. These parameters can be set manually using routines I'm about to show you, or alternatively, there is an AutoAligh routine that will analyze the batch and attempt to find them for you. So set the beam center position in meters. That centers the FFT window and sets the definition of the center of the field. You can set it for either the X or Y axes and for each polarization component. You can specify the reference wave angle called the tilt. That's in units of degrees by default. And again, you can specify it for the X and Y axes and for each polarization component. This sets the center of the window that will be inverse Fourier transformed. Optionally, you can also specify the defocus of the reference wave. So if your object wave and your reference wave have some relative defocus that you want to remove, you can also specify that in diopters, inverse meters. In order to set the dimension of the Fourier transform that takes the camera frame into Fourier space, and the inverse Fourier transform, which takes us from Fourier space back onto the camera plane as the reconstructed field, we have these two parameters. That's FFT window size and Fourier window radius. FFT window size is defined in pixels, width versus height on the camera plane, and that window will be centered at the beam center position I specified earlier in meters. The window for the inverse Fourier transform that selects the off-axis term and also the dimensions of the reconstructed field isn't specified in terms of its pixel dimensions. It's specified in terms of an angle. So that is, you select a window of a certain radius in Fourier space specified in degrees by default. Now numerically, the inverse Fourier transform will be a square or rectangular window rather than a circular window, but any region outside that Fourier window radius will be zeroed. And as with all dimensions, it will be enforced as a multiple of digHolo_pixel_quanta, which at time of recording is 16, meaning that the dimensions of your reconstructed field, but also your initial FFT, will be multiples of 16. It does that so that everything fits into a whole number of AVX 256-bit vector registers. As I said before, you've got the option to specify these parameters manually. Perhaps you already know the numbers or a good starting guess of those numbers. Those routines I just showed you are how you can manually set those parameters. But you can also call the AutoAligh routine, and that will analyze a batch of frames and attempt to guess the parameters for you. In that case, you set a flag 0 or 1, specifying which parameters you want the AutoAligh routine to optimize, and then you call digHoloAutoAligh. It doesn't automatically guess the size of the initial FFT, that is the FFT window size parameter. You have to set that yourself, or it'll just end up being whatever the default is. If you want to do a Hermite-Gaussian modal decomposition or some sort of related modal decomposition, then there's also some additional parameters you'll have to specify, some of which can also be set manually or estimated by AutoAligh. Primarily, you'll need to define how many modes you want in your decomposition, the basis group count, or more specifically, up to what mode order do you want to include. And you'll also have to specify the waist radius of your basis in meters. Basis group count specifies the maximum mode order in the mode decomposition. These are the Hermite-Gaussian modes of index mn, and the mode order is m plus n. As you keep including more orders, you'll keep including more layers in this pyramid here, starting from the top, working down. Basis group count of 0 will turn off modal decomposition altogether. Setting it to 9 would work out to give you the total of 45 Hermite-Gaussian modes corresponding to the modes we're looking at here. This number you have to specify yourself, it won't be guessed for you. The waist radius is just the normal waist parameter from Gaussian beam optics that you'll find in the formula for a Hermite-Gaussian beam. It specifies the scaling of the basis. The waist can be set manually, or AutoAligh will attempt to guess it for you. And many of these parameters, including the waist, have so-called pole locks that you can also define. So you might want both polarizations to have, let's say, the same waist. So you can set the pole lock to 1. Then the waist for the two polarization components would always be the same. But you can also set the pole lock for things like the tilt and the defocus. So if you know your reference beam should have exactly the same tilt and exactly the same defocus for both polarization components, then you can lock that in and they won't be tweaked independently. If you're looking to use a basis other than Hermite-Gaussian, you can also specify a custom transformation matrix that will map the Hermite-Gaussian basis onto whatever basis you want. Now natively under the hood, the basis the field is actually directly being decomposed in is always Hermite-Gaussian, but through an additional matrix multiplication, it can transform that into some other basis. A Laguerre-Gaussian basis option is built in. It effectively just calculates that transform matrix for you internally. Or you as the user can specify your own basis that takes a certain number of input Hermite-Gaussian modes and transforms that onto the desired number of output modes in your basis. So if you want to transform into, say, a Bessel basis, you could define a matrix that maps the Hermite-Gaussian modes onto the Bessel modes and input that, and then it would decompose in the Bessel basis. All right, finally, so all the parameters are specified, either manually or automatically using the AutoAligh routine. And now it's time to actually run the digHolo processing pipeline using those parameters. The routine you call is digHoloProcessBatch, and you can just keep changing the setFrameBuffer pointer and all the pixel data in the memory itself that setFrameBuffer points to, and it'll process those frames. Actually, if you've just run the AutoAligh routine and the frames are the same, you won't really have to recall digHoloProcessBatch, as the processed frame data will already be available from the last AutoAligh call. But whenever you update the frames, you'll have to recall digHoloProcessBatch. But if the digHolo parameters like the tilt, beam-center, defocus, waist haven't changed, you don't need to reset them manually or automatically when you change frames. Okay, so you just set it up with either manually or with digHolo AutoAligh, get all the parameters, then just keep feeding frames in and keep calling digHoloProcessBatch. Under the hood, ProcessBatch just calls some subroutines that do the Fourier transform, pick off the off-axis window, and do the inverse Fourier transform, removes any residual tilt and defocus of the reference wave, and then optionally extracts the modal coefficients if you've specified to do so. It returns a pointer to the modal decomposition coefficients for each frame in the batch. If you've specified set basis group count as 0, that is you don't want any modal decomposition, then it will just return a null pointer. And that function also returns the number of frames processed in the batch count, as well as the number of modal and polarization components. That is, it returns the dimensions of the coefficient array that the function returns. You can also call digHolo basis getCoefs. That will return the same thing, but it doesn't trigger another run through of the processing pipeline. So that routine assumes you've already processed the batch, you just want to get the coefficients which are already there. If you want the actual fields on a pixel by pixel basis, then you'll have to call digHolo getFields, which will return the fields themselves, but it'll also return in the arguments the batch count, the polarization count, a pointer to an internal array containing the x and y axes for the fields in meters, and the width and the height of each polarization component in pixels. The fields will have been rearranged relative to the original camera frame in such a way that the two polarization components, if there are two polarization components, are now adjacent in two separate chunks of memory, rather than being interlaced as they would have been in the original raw camera frame. If you're interested, you can also request some calculated values for your processed batch, things like the total power, the center of mass, the maximum value, the effective area, etc., on a per frame, but also on a sum or average over the whole batch. Things like the total power, the center of mass, the maximum value, the effective area, etc. You can request that on a per frame basis, or also it's available as the sum or average over the whole batch. There are some simple plotting routines that are available, plotting things like the fields, camera frames, the Fourier plane, with some sort of basic annotations on it. Of course, you can also do your own plotting using the data that digHolo returns, but there are some basic plotting functions it can do for you. digHolo can be called from the command line as an executable rather than as a library. You specify the file name path to a tab delimited text file, and it basically just calls this function internally. And inside that text file, you can set all the parameters. You can feed in data like camera frames as raw binary files. If you don't specify any input frame data, it'll just generate a test set with the parameters that you specify elsewhere in the file, like dimensions and batch count, etc. There's an example text file provided as well. There's a printout console that prints digHolo's internal notifications and information. You can have that print to standard out, or you can redirect it to file. For example, if the console's not visible, let's say, maybe you want to view it in a file instead. And you can set how verbose you want the printout to be. Or you can set it to 0 and make it silent and it won't print out anything other than very deep errors. There's a simple test frame generator, both an advanced interface version and also this simple version. You request the number of frames, the dimensions of the frames, the pixel size, polarization count, and the wavelength, and it'll just create some simulated off-axis digital holography test frames for you. There's also options for specifying wavelength-dependent batches. We often do experiments in our lab where we sweep the wavelength of the source as we measure the frames to get things like frequency or time domain analysis. And these functions let you specify the relevant parameters for that. Averaging is also supported. In this case, you can have multiple frames all measuring the same thing, and then digHolo will average them together by adding them together constructively, so that is in phase. So it'll assume that there's some phase drift in your reference from one frame to the next, and it'll calibrate that out by summing up all the average frames in phase. Routines for calibration. Maybe your reference wave isn't a good plane wave. Maybe it's got some non-uniform intensity or phase. You can cal that out. Or maybe every frame in your batch isn't the same. Maybe every frame was captured at a different camera exposure or a different source power. Or perhaps there's some delay or phase dependent factor you want to remove. You can cal all those out as well. And just finally, there's routines for benchmarking. A benchmark Matlab script is provided in the examples, but there's routines for setting the number of available threads or estimating the optimal number of threads to use, running benchmarks, or setting the underlying FFTW planning mode behavior. Okay, that's it. Thanks very much. Further information is available in the description below this video, and enjoy using digHolo high-speed off-axis digital holography library.